One, two, one, two, one, two, one, two, one, two. Woo! So it's been a kind of an extensive one, and yes, we've seen how the logic that we used behind it, the logic we used to get where we were trying to go to. But one thing we haven't found is we've not even spoken about rather is the complexity, which is the meat of the matter, the bone of contention. Because when we're looking at as we've throughout the series, we've seen that the main stuff is to understand the complexity and how this complexity helps us, better a system, basically make a system work more efficiently, right? Because we are talking of small numbers here or small examples here, but in an ideal system, we are going to have loads and loads of values coming in, and that's basically what we are trying to look at. So we are going to jump straight into complexity and see what exactly our complexity will be saying. Now we start with the find path, right? That's how we find the path of A and the nodes, the individual nodes. That's D and E from our this thing. So we're just going to go through. We're going to see how this find path function and how what it takes to give us the path of these guys, that's the L and R. So we say time, because it is a BT and not a BSC, we have to search all to find the node in the worst case. And the worst case is that we go around the entire tree. So basically, we could see here that in find path, we don't have any, we just have to just keep searching. When we search through the left, we search through the right. And in the worst case where maybe we have a skewed list, right? Or maybe even with this list self, let's say we are looking for, what we're looking for is C. We first go to the left, we search all the left and the right, and then we'll come back here and then we search here before we find. So basically, the worst case scenario is searching this O of N, because we could go through the entire list. And our space is O of H, because we are holding directions and popping it. So basically, when we come here, O of H being the height of the list. So the worst case is that we'll find a list that is here. So let's say we find this guy here, but we're looking for this guy over here. We come here, we look for this guy, we come here to the left again, but we don't find it and we hit a none. So we return, we pop D from here, we come back here. So basically, the last place we could go would be the height. The maximum amount of values that this list would ever hold would be the height of the tree. So hence why we have a space O of H. And that's it for the find path. So we have an O of N and an O of H for the find path. Now we come to the lowest common ancestor function, and we look at the complexity. Now find path has already, so we say we say find path has already given us some O of some complexities. So we are going to also have that in mind. So we say time O of N, but O of N plus H, because we do find path twice, right? And then we iterate the tree a third time to find where our paths, that's our paths align. I think this is align, right? And that's the worst case. And that the worst case is the length of the list. So basically, the worst case is the length of this list, because so when we what do we mean by that? So after we find this guy, O of 2n, because we're looking for two paths, the path to this guy and the path to this guy. So those two could take O of n times, and then the second the last iteration now is that we now follow through left, or left, right. And in that last iteration, or the while loop, the worst case is that it will take us straight to the bottom of the list, which is the height of the list. So that's why we have H over here, right? Yeah, we have H over here. So now, because of the way complexity works, it takes away constants, and basically, yeah, it takes away the constants, and basically takes the highest node, the highest iteration, or the highest complexity at the time. So basically, that's why we have O of n as our resultant complexity here. But we can see this is the packed complexity. And then space, find path returns O of h, but obviously our lowest this holds no values. Is basically one iteration and holds the counter. So basically our O of n h, our complexity will come from the path, that actually holds an array that extends, that builds to the max, to the height of the list. And basically our final guy is basically O of n and O of h, right? So O of n and O of h. So that's the complexity for the brute force. And this, we could immediately tell that even before looking into the optimization, we could tell that there is the fact that we are searching through the entire list and holding these values and coming back to come and search through the list, because we're doing like 3 searches through the list, or 3 iterations through the list before finding this lowest common variable. It's a bit of a wild one. So the next stop Next up, we are going to be looking at, okay, how do we then break this down and make it more efficient, because that's the entire goal right here. So that's what's up next.